All right, here's your last example for your vectors unit. And this is going to be an application. This is saying a Boeing 737 aircraft maintains a constant airspeed of 600 miles per hour headed due south. Then it has this jet stream acting on it, which is 60 miles per hour in the northeasterly direction. Now, this is not my favorite description. That's pretty vague in my mind, but I'll show you what they mean because you'll run into it in a homework problem. So before I read anything else, I'm going to try to get myself some visual. And so I'm going to create, we have north, south, west, east. And we're going to draw these vectors in standard position to make our lives easier. So we know we have one vector, because remember vector, we have to have magnitude and direction. So one vector is that aircraft, okay? It's traveling at a constant airspeed at 600 miles per hour, and it's headed due south. So I'm going to change colors. So we have this aircraft vector. All right. We know that it's 600 miles per hour, okay? And then we can figure out the direction because it's due south. Then we have this other vector that is northeasterly, so that's why I'm heading this way. And I know this doesn't look accurate because they look kind of the same length, but it works. Because this one is only 60 miles per hour, so it should be way shorter than the other one. So when it says northeasterly direction, I'm going to go ahead and actually I am going to put the 60 under here. All right, just remember, this is bearing. We learned that when we first met each other. And your bearing is always attached to either the north or the south line. So 45 degrees, I am definitely doing an assumption there. That's why it's not my favorite descriptor. But when your text says northeasterly, it's saying it's going right in the middle of that. So if it said southeasterly, it would be, down here. But that's not where it is. Okay, so think about this. You have this aircraft that is flying due south, and then this jet stream is pulling on it, right? So think about it. Should this aircraft then, when we actually figure out the actual speed of it, do you think it would be going slower or faster? And hopefully it makes sense that it would be going slower. All right. So think about like when you fly from East Coast to West Coast, it's much faster than from West Coast to East Coast if you've done that flight. Okay, so what this is doing is it's going to ask us in steps. So it says A, express the velocity V sub A of the aircraft and the vector for the jet stream in terms of I and J. So I'm going to go ahead and do A. Okay, so here's our vector V. You can make it bold, but that's kind of hard to do, so we like to put a vector above it. And this is for our aircraft, that's why it gets that sub A. So remember, just from the previous notes, you put your magnitude out in front, and then it's cosine of the angle. Now you can use radians or degrees, whatever you feel comfortable with. I'm going to use degrees since I just decided that when I put 45 degrees. Sometimes it does make it a little bit easier. All right, so cosine of, now you want to think about this. Where is that vector heading? It's due south. So you have options. You're either going to tell me 270 degrees or negative 90 degrees. Either one works. And this is I. And then plus sine 270j. If you forgive me, this should be a good old vector symbol. Okay, so let's go ahead and clean that up. We know cosine of 270 degrees is 0. We also know that sine of 270 degrees is -1. So if I distribute that 600, well, 600 times 0 is just 0. So I could leave off the I. And then 600 times this guy, this would be -600j. And so that is your vector in terms of I and j for your aircraft. You could have just looked at that vector and not done that work. You could be like, well, no, I know it's heading due south, so that's why it's going to be negative. And it's just a vertical movement, so that's why I only have a j. Now our vector for the wind, the jet stream, well, our magnitude is 60, and our direction is 45. So let's go ahead and clean that up. And this is why we have to know that beautiful unit circle. Cosine of 45 degrees is √2/2. And sine of 45 degrees is also √2/2. If I distribute that 60 divided by 2 is at 30. So I get 30√2i plus 30√2j. And this is your vector for your jet stream. Oh, they're saying for wind. Okay. Now for B. Find the velocity relative to the ground. So what we want to find there is we are going to find a vector. Let me go change home. So for B, I gave you an extra sheet here, so if you need it. So now for B, we want to know what is happening when this jet stream is acting on this aircraft, okay? So another way to put this is you're looking for the resultant vector, which Wendy discussed, which is A plus W, which is another name for our vector relative to the ground. So we end up getting, we're going to add these two vectors together. It was -600j plus our jet stream. That looks kind of ugly to me. You can leave it like that if you really, really want to. But it is nice to combine like terms. So these j's are alike. Unfortunately, one is with a rational and one is not. Or irrational, I should say. So I have 30√2i, because our i's are written first, plus, and what I'm going to do, and you don't have to do this, but -600 plus 30√2, that is all j. I do not, please, 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 do not write it as a decimal unless my math lab asks you to, but it will royally mess up your end result if you start rounding at this point. All right, so this is known as your resultant vector to tie it into what we learned earlier. Okay, so now what C is asking for is find the actual speed and the actual direction. So again, if this thing is pulling on this thing, really how fast is this airplane going and really where is it heading? Okay, so that's why we would have an airplane to help us correct this, so we would end up at the same spot that we wanted to. So what we need to do is it says find the actual direction and speed. Well, speed, and you can do direction first, but speed is magnitude. So remember, your magnitude is the square root of your vector. with your I squared and your J squared, just from Pythagorean theorem. And what I'm going to do now is I'm going to rely on Desmos. Let's go to Desmos Scientific. I think it'll be better. So I'm going to put in here, actually, let's just put in exactly how I see it. Clear all, okay. Square root, parenthesis, 30 root, no, 30 root 2. I'm going to get out of there, close that parenthesis. I'm going to square it, plus, parenthesis, negative 600 plus 30 root 2. So really pay attention to where your parentheses are. Close that, and that's squared. So what we end up getting here is that's our actual speed, 559.19. So our actual speed is 559.19. Pay attention to how the problem started, and it was in miles per hour, because sometimes it's in kilometers. Okay, and hopefully that sits well with you, right? Because this wind is pulling on this aircraft, so it's going to slow it down. Now, to find the direction, remember we used inverse tangent. Remember that is opposite over adjacent. The other way to think about that is your vertical movement over your horizontal movement. Again, leaving it like this and not saying it is a, not putting it as a decimal, because it will really mess you up. Also, please don't be inclined to cancel out those 30 root 2's. This 600 doesn't have one, so you can't do that. So I'm going to rely on my calculator. I'm going to make sure I'm in degrees, so I changed it to degrees. Inverse tangent. I'm going to put the division first. So it was negative 600 plus 30 root 2. And then it's divided by 30 root 2. Okay. So this tells me negative 85.65 degrees. But remember, negative 85 point, what was it, 65? Yeah, 65. But remember, your calculator, bring it back to chapter 6, is only programmed to give inverse tangents from negative 90 to 90, right? Because otherwise it's not a function. But this is really important. Bringing it back to when we first met each other, you have to give direction in terms of bearing, okay? Because this is an application problem. So yes, if I'm going to go back to our diagram, what is happening here is we found this resultant vector is being pulled this way. Okay, so this is actually where the aircraft is heading. And what they're saying is from here to here is negative 85.65 degrees, which that's true. But when we're talking about direction, and especially when we're dealing with aircrafts, they use bearings. So think about what could you do to that value to actually get out the bearing you need, which is this acute angle, remember? And that would be, well, you would add it to 90 because that would complete this whole portion. So it's not always adding 90. You got to think about it visually. Sometimes you might do something different. So I'm going to go back down here. And really, I'll change pens. It's negative 85.65 plus 90 degrees. So we end up getting 4.4 essentially. And so what you want to say then is the actual speed of the aircraft is about, and I like to say about because I did some rounding, 559.19 miles per hour. And the actual direction, now be careful with this, I need bearing, is about, now if I go back up here, if this is the angle we're looking for, right here, that's attached to your south, right? And it's heading east. So that's why I'm going to say it is about 4.4 degrees east of south. Okay, see you next time.